Okay, this is part 2 of basic passive elements, where we will be discussing the capacitor. A capacitor is an interesting element. It is a passive element, but it doesn't dissipate energy as resistors do. But they have the ability to store energy, and it stores energy in the form of charge stored on two conductive surfaces separated by an insulator. So you can think of a capacitor, well, since it's two conductive surfaces separated by an insulator, we actually draw the symbol as such. So we break the wire and draw two plates, is what this means, in parallel with one another. And in between, you have an insulator. I'll annotate that with the red. Okay. So that if you wire this capacitor to a voltage source, V, what you get is net positive charges on one side and net negative charges on the other. See, as electrons are going to want to flow towards the positive side, they want to be attracted to the positive terminal of the voltage source. They are stopped at the bottom plate because of the insulator. They can't flow through the insulator. Likewise, net positive charge would be stored on the top surface. In that way, capacitors then store the charge on these surfaces. So what's interesting to note about these in order to quantify the ability for a capacitor to store charge is we look at the area. Let's see. The area of the parallel plates, the distance that they are separated by, and then the quality of the material in between to separate those charges. And we call that the permittivity of the insulator. You can think of it as a measure of the ability of the material to store charge, or the ability of the insulator to kind of sustain an electric field that is generated across it by the separation of the charges that want to combine with one another. The permittivity is in units picofarads per meters, where the capacitance itself is what what is measured in the unit of a farad, which is a capital F. We usually reference permittivity to that given in vacuum. So if the insulator was a free space in vacuum, the permittivity of that would be approximately 8.85 picofarads per meter. So we again reference all materials with respect to this quantity. For example, the permittivity of silicon is 11.68 times the permittivity of that in vacuum. Okay, so as I mentioned on the last slide, the electric symbol for a capacitor, we literally break the wire and put two parallel lines to indicate that this is a capacitor. Just as in with a resistor, we use the passive sign convention to annotate. So a capacitor can have a voltage across it and a current through it. And as we separate those charge by tying that to a voltage source, for example, we note that the charge polarities are separated by the insulator, which then generates an electric field in this direction, which sustains the storage of the charge. So charge is stored via the electric field. So based on that physical drawing from the last slide, we note that the area of the parallel plates is of interest. The larger the area, the more capacitance, because the more physical space that we can store the charge. But capacitance is inversely proportional to the distance. So the larger the distance between the two parallel plates, the less capacitance. Makes sense because it permits less electric field, for example. The permittivity through the field is less so because we separate the plates out. And then constant of proportionality of the capacitance would be this permittivity, which we multiply the capacitance term by. Checking units, you see that given the permittivity in farads per meter, area in meters per square, distance per meters, we do get units of farads left over for capacitance. So the capacitance can be defined in terms of the current through the device, as well as the voltage across the device, just as in a resistor. However, instead of Ohm's law, we have a slightly more complicated relationship. We have a differential relationship between the two, in that given a alternating current source, it must be alternating, as we see by this expression. The current equals the capacitance times the first derivative of the voltage with respect to time. Note that these must be functions of time in this case. We'll see the implications of one of these parameters being constant in a moment. So I equals C times dV versus Vt. Okay, so let's examine this expression in a little more detail. The way to think about a capacitor is that, well, since we noted that the storage of charge on the parallel plate separated by the insulator creates an electric field, which is proportional to the voltage, we can expect that as we move charge on or off of the capacitor, we would expect a change in the voltage. So the movement of charge on or off the capacitance is done via current, which we know then is going to be proportional to the change in the voltage, so which is hence the first derivative term of the voltage with respect to time. Time's, of course, a constant of proportionality, which is what we describe as capacitance. So we can rearrange this equation a little bit to explore this a little bit further. So multiplying by both sides by dt and then integrating, we see that the capacitance times the voltage, which in this case integral of dV, is going to be equal to the integral of the current with respect to time, which is what we have defined as charge. So we can rewrite this expression as Q equals C times V, written in two different ways. In other words, the capacitance describes the amount of charge stored per unit volt. So as charge is moved onto into a capacitor via current, the voltage will increase proportionally, hence the time's rate of change. Okay, so what happens when the voltage across a capacitor is constant? So in this case, we're going to take a capacitor. Note that I drew the symbol a little bit different in this case. I have a flat line for the top plate and a curved line for the bottom plate. This is the same thing. It's just a capacitor, but what this notation implies that the curved plate implies that it has to be the lower polarity. So we're implying that this is the negative side of the capacitor. It has to do with the type of capacitor utilized. Certain capacitors and the way they were manufactured have to have the polarity set up a certain way, otherwise you could damage the insulator. You still treat those the same way, you just note that this dictates how you have to wire the capacitor up. It's not symmetric. So if we wire that up to a constant voltage source, so a DC voltage source, we have voltage V0 across that capacitor. Looking at this expression that I equals C dV dt, we note that dV versus dt is 0 because the voltage is constant, therefore the current must be 0 amps. So even though we have a voltage across the capacitor, it's constant, therefore there is no change in the charge stored in a capacitor, therefore there is no current moving on or off of the capacitor, which would be changing the amount of charge stored. We often will say that capacitors act like open circuits to DC, to direct current, because when we have zero current going through an element, it's like breaking that wire, which is what we call an open circuit, which implies 0 amperage. And what about a sudden jump in the voltage? So a step response. So in this case, I've wired the capacitor up to an AC source, script V here, so that I'm going to have a current I that is a function of time going through the capacitor. But V is defined as a step function, so in this case I'm just saying at time 0, it changes from some initial value to a value V0 instantly. And the first derivative of this function we note is infinity. Therefore, this implies that the current through the capacitor at time 0 must be infinite. So a step function, regardless of the value of this step, requires an infinite amount of current in order to do so, which is not possible. So we note that it will take there will be some finite current available, which means it will take some finite amount to charge. And the reality is, if we try to do this, let me draw it here in blue, what you would get is you try to change the voltage source instantly, but the voltage across the capacitor would look something like this. It turns out that would be exactly an exponential function, an exponential rise function, and we'll see that later. but it takes some amount of time to actually move the charge onto the capacitor. In other words, it will not be an infinite amount of current available to you, so it will take time to move it, to change from one voltage state to another. So we can say that capacitors resist changes in voltage. And finally, we can rewrite the expression that I equals C dV versus dt in order to solve for some other parameters. So let's explore first what it looks like to solve directly for the voltage across a capacitor. Rearranging this expression a little bit and then integrating both sides, we can write that the voltage across a capacitor is given as 1 over C times the integral of the current with respect to time from some initial time point to time t. And since we're integrating, we need to know the initial start point of the voltage across the capacitor. Again, it's relative to a start point because current is just the first derivative. It's the rate of change of voltage. So it's going to be 1 over C times the integral of I plus the initial voltage that was across the capacitor to begin with at time t0. And then we're always concerned with the power. So in this case, it's not power dissipated, but it's power stored by the capacitor, or delivered to a capacitor, I guess is the right way to describe it. And we know that P is just V times I. If you can't remember the specific expression for a given element, you always know that it's V times I, and you can figure it out. In my opinion, memorizing expressions like this, if you tend to make mistakes with memorization, just don't do it. P equals VI is something that I think is easy to remember, and so you can always end up figuring it out and compute it, regardless if you remember the specific expression. So knowing that P equals V times I, we can take the simpler of the expressions, which is I equals C dV dt, and sub that into here, and we see that P equals V times C times the first derivative of V with respect to time. It's a differential relationship there. So it's got V and dV in the expression together. And then energy, so what I'm going to derive here is the change in the energy stored in the capacitor. So in this case, again, capacitors are passive elements, so they cannot supply power indefinitely. They can temporarily, as much as we've got charge available in the capacitor, but we know as it releases that charge, we could have negative power temporarily, but we know that that would eventually go to zero. So hence it's still it's a passive element. So if we derive it as energy stored, so that'd be power delivered to a capacitor, we know that we would expect that the power would be computed as a positive value. Hence the energy being stored in it would be positive. So I'm going to derive that as the change in the energy. Would just be the integral of the power, given the energy-power relationship, from T0 to T. Rearranging and subbing in the former expression, I get C times the integral of V dV versus dt times dt. We see that the dt's cancel out, leaving over V times dV, which changes the boundaries at which we need to integrate, since we're now integrating with respect to the voltage. Therefore, instead of time 0, we're integrating from the initial voltage at time 0 to the final voltage at some time t. So it's C times the integral of voltage with respect to voltage from the initial and the final voltage points. So if we perform that integral, that is a pretty basic integration, and where we get then 1/2 times C V squared evaluated between those 2 points. And so if you take that last expression, and if the initial energy was 0 joules, then we see right away that the energy delivered to a capacitor is just 1/2 C times the voltage squared.